Grade 12 Function, Section 2.5. Today we'll be talking about solving problems involving rates of change. So we'll first look through some examples. So this one, for example, Leonard is riding a Ferris wheel. His elevation, h of t, in meters above the ground at time t in seconds can be modeled by the function h of t is equal to 5 cos times 4 times t minus 10 degrees plus 6. So Shu thinks that Leonard will be closest to the ground at 55 seconds. So do you agree? Support your answer. Okay. So the first thing we're going to do is find his average rate of change in elevation. Now, why is this important? Because we want to know his height or his distance from the ground at 55 seconds. Now, in order to find that, we have to use, in other words, looking for the instantaneous rate. So in order to find that, we're going to have to use average rates and then approximate an instantaneous rate. So first, our first piece is looking at the average rate of change at a value that is smaller than. So we're using a 54 and 55 seconds. And this is our resulting average rate of change using those two values. And then we're going to use a piece that is bigger than our desired rate of change. So we're going to use 56 seconds and 55 seconds. And that's going to give us this piece right here. And so then we're going to say that a minimum could occur at 55 seconds. And we're going to use our values 54 and 56 and 55. And as a result, we get the instantaneous rate of change to be 0. Now, how do we get that? We get that because we average out these two pieces right here. So we're averaging out the value we got from the point that is smaller and from the points that are bigger than our desired time, which is 55 seconds. And as a result, once we average this out, we get the instantaneous rate of change to be 0. And since h at 55 is less than both h at 54 and h at 56, he's closest to the ground at 55 seconds, just as he predicted. Okay. So example 2, we're going to use an algebraic strategy to identify the location of a minimum value. So show that the minimum value for the function happens when x is equal to negative 2. Okay. So in order to do this, we're going to estimate the slope of the tangent at the curve to the curve at a is equal to negative 2. And we're going to use the definition that we learned in the previous lesson. And once we do that, we're going to estimate the slope of the tangent to the curve when x is equal to negative 2. So we're going to replace h with really, really small values. So we're going to use a small value that is one that is a little bit smaller and one that is a little bit bigger. And once we do that, we then take the average of these two rates and find it to be 0. And then we put in we're going to find the y values at these points, one that's a little bit bigger, one that's a little bit bigger, and one that's a little bit smaller, and one at that point itself. And therefore, we then know that since the slope of the tangent is equal to 0 when x is equal to negative 2, and since the values of the function when x is equal to negative 2.1 and x is equal to negative 1.9 are greater than the value when x is equal to negative 2, a minimum value occurs at x is equal to 2. Okay, example 3. So this is going to use a graphing calculator. And so Tim has a culture of 25 bacteria that is growing at a rate of 15% per hour. He observes the culture for 12 hours. During this time period, when is the instantaneous rate of change the greatest? Okay, so the first thing we're going to do is we're going to find an algebraic model. So that's what they're doing here. Is we're going to find the model, and we're going to find that. Once we find that, we're going to then graph it in our graphing calculator, and we're going to graph it within the given domain. And as such, we can see that the instantaneous rate of change is greatest near the end of the time period. How do we know that? Because the graph is increasing at the fastest rate at that point. And so then we're going to estimate the instantaneous rate of change between time at 10 and time at 12. And we're going to draw tangent lines at those 2 points in order to find it. And then once we average those out, we get the instantaneous rate of change to be the greatest at 12 hours. So in summary, the instantaneous rate of change is 0 at both a maximum point and a minimum point, right? And that's what we saw in our first example. Since we know that the instantaneous rate of change was 0 here, that must mean that it was probably at a minimum point right here. So if any of you are familiar with derivatives, the same thing occurs, is that when a derivative is 0, we know that we're at a max or a minimum graph. And as a result, the tangent lines will always be horizontal. If the instantaneous rate of change is negative, before the value where the rate of change is 0, and positive after means it's minimum, which is what we see right here. And if it is negative, then positive, we know that it's maximum. Perfect. Okay. So now some examples. So We have this question here. The cost of running an assembly line can be modeled by the function c of x is equal to 0.3x squared minus 0.9x plus 1.675, where c of x is the cost per hour in thousands of dollars, and x is the number of items produced per hour in thousands. So the most economical production level occurs when 1,500 items are produced. Verify this using the appropriate calculations for the rate of change in cost. So we're going to use a definition of a derivative. That's actually what it's known to be. And we're going to set h to be a really, really small value. So we have here c at 1.5 and c at 1.501 gives us our two resulting y values. And then we're going to calculate the rate of change based on that. So therefore, when 1,500 items are produced, the instantaneous rate of change equals 0. Okay. So this is actually good because that means that it's the most economical thing, and that means that there are 1,500 items produced. Now again, for those of you who know derivatives, you know that if you set the derivative equal to 0, that will give you your max or min, right? So it's similar. It's a similar concept here. That's how we know it's most economical, because the derivative is 0, and that means that there's no change occurring at that point. So that's how we know that there's 1,500 items produced. Okay, so then for each function, the point given is the maximum or minimum. Use the difference quotient to verify that the slope of the tangent at this point is 0. So we just went through example A here. You have our 2 points given, and we have our main point given, and we're going to use again a point that's a little bit smaller and a little bit larger than our given point. So what we see here is that the left, once we calculate this through, the left side of this is the slope that is given. That means that our left side of the function has a negative slope, and the right side of the function is a positive slope. And as we saw before in our summary, that means that if it's a negative slope and a positive slope, that means we have a minimum here, which is exactly what happens with our given function. So that means that the point -6, 10.5 is at a minimum. So to summarize, we talked about maximums and minimums using rates of change, and we talked about how when there's an instantaneous rate of change of 0 at a function, that means that it's at a maximum or minimum. And we also talked about how in order to have a minimum, you need to have a negative slope and then a positive slope. In order to have a maximum, you need to have a positive slope and then a negative slope. We also went through some examples, this one being almost an optimization problem where you found that the instantaneous rate of change when it's 0 will give you the most economical result. And we also went through an example that showed us how to think graphically, where if you have a negative slope followed by a positive slope, this point would be at a minimum. So with that, thank you for watching. I hope you enjoyed this video, and as always, if you have any questions, feel free to contact us at passionate